Hello, and welcome to the presentation of this work done with collaboration with two amazing colleagues of mine, Lemon Poncelet, who was a postdoc at our group and has now moved back to France, and Nicolas Chiftis, who is a senior researcher at the Rice Institutes of Sweden. I am the guy in the middle. So this work was done under the aegis of the ASSIST project, a 5-year research project funded by the Swedish Foundation of Strategic Research. The overall goal of the ASSIST project is to investigate techniques and tools for securing IoT software. As a demonstrator, the project has promised to strengthen the security aspects of Contiki-NG, a next-generation operating system for IoT platforms. An obvious idea on how to achieve this is to employ fuzz testing, also known as fuzzing, to its code base. Our paper, published at the AC, documents this effort and reports our findings regarding the efficacy of a total of 8 state-of-the-art mutation-based and hybrid fuzzers in exposing vulnerabilities and bugs in various layers of Contiki-NG's network stack during a period of more than 3 years. As a byproduct, we propose an open-source bug suite for evaluating fuzzers on real-world software vulnerabilities. Finally, using this suite, we also measure the impact that sanitizers have on fuzzers' effectiveness, effectively answering the question, should we use or should we not use a sanitizer when fuzzing? As mentioned, the code base we target is that of Contiki-NG, an open source operating system designed for resource-constrained IoT devices. Its main feature is its low-power IPv6 stack, which includes a variety of standard communication protocols implemented in a compact manner. In the figures that you see in the slide, you can see the various layers of Contiki-NG network stack. Incoming packets enter at the physical layer, down at the slide, and have to pass the checks of various other protocol layers to reach the topmost application layer. Each of these protocol implementations can be a possible attack target for anyone who has the capacity to inject packets into it. One important point to keep in mind is that when fuzzing the Contiki-NG network stack, one has to consider this layer architecture, decide on the seeds to use. We have decided to start the fuzzing from the IPv6 and then from the 6LoWPAN layer. Back in the middle of 2018, we started fuzzing using AFL, which is a popular and effective coverage-based gradebook fuzzer, which has since been used as a component in many other fuzzers that have been published in the literature and that we examine in this paper. When using AFL for the first time in its code base, it's quite easy to be impressed by the ease of use and effectiveness in detecting bugs. For example, on this slide, you can see the first experiment we ran. We ran AFL for 1 hour, and this has produced an impressive number of more than 68,000 crashes, 55 of which are labeled by AFL as unique. Sadly, our initial excitement did not last very long. As it turns out, all these 55 unique crashes correspond to just one, and actually a relatively shallow bug in Contiki-NG's code base. Once this bug was fixed, all these crashes simply vanished, and we had a hard time detecting other ones with the simple use seeds we were using back then. This brings us to some of the lessons that we learned. The first lesson is something which by now is quite well known about fuzzers, namely that the number of so-called unique crashes is not a good measure for a fuzzer's efficacy. Instead, it's the number of bug fixes, and arguably also their severity that matters. So, as a suggestion to the software engineers, we argue that one should stop a fuzzer, at least those that rely on AFL, quite soon after it has come up with the first bunch of so-called unique crashes, try to understand and fix these problems, and then I run the fuzzer to check whether similar unique crashes still exist in the code base or not. We have used a number of mutation-based fuzzers. AFL is not the only one that is around. On this slide, you can see 4 of them, which are the ones we have used in the paper. You can also see some brief information about the techniques that these fuzzers are using in order to select and schedule the mutations that they employ. Of course, more information about them you can find in our paper or in the sites of these fuzzers. The main advantage of mutation-based fuzzers is that they explore the program at nearly native speed. Their main disadvantage is that their search is quite naive, and they have a hard time exploring many of their program's branches and also many of its paths. A more sophisticated software testing technique is symbolic, or sometimes called concolic execution. It's quite effective in exploring branches that are guarded by complex conditions, but to do so, it typically has to call a constraint or SMT solver, and thus it's significantly slower. Various researchers have proposed combining a symbolic execution component with a mutation-based component in order to get the advantages of both of the approaches. The corresponding fuzzing tools are called hybrid fuzzers. So hybrid fuzzers, hybrid fuzzing is a trade-off. On the one hand, the hybrid fuzzer can achieve increased code coverage, hoping that this will detect more bugs. But on the other hand, it executes fewer program runs given the same time budget. Thus, to be effective, a hybrid fuzzer tries to use the mutation-based component for as long as possible, keep track of the coverage that is achieved, and when this coverage stops increasing, resort to the symbolic execution engine to provide inputs that hopefully now we will exercise some new paths and so on. So these are the 8 fuzzing tools we have used in this paper. 4 of them are mutation-based and 4 of them are hybrid fuzzers. You can see their names: AFL, AFL Langfast, Songfuzz, mopt with AFL, Angora, QSIM, Intriguer, and SimCC. This table, taken from our paper, has too much information, so don't try to read it. What it shows is the 18 vulnerabilities and bugs we discovered and fixed using test fuzzing. The bugs are shown in chronological order, which roughly corresponds and correlates to the difficulty of detecting them. Each of these bugs comes with a pull request that fixes the bug and the IDs of 2 commits, one before the fix was applied to the code base and one after the fix was applied to the code base. So for each of these commits, we know that the code base without the commit contains a number of bugs, and the code base after the commit contains one less bug, namely the one that was fixed. So what we do in our experiments is to check out versions of Contiki-NG code base based on this commit history and check whether each fuzzer is able to expose the bug of interest or not in a series of 10 24-hour trial runs. Finally, note in this table that most of our bugs have associated CVEs with them. So this brings us to the main research questions that we try to answer in this paper. The first of them compares mutation-based and hybrid fuzzers. Is hybrid fuzzing a more effective technology than mutation-based fuzzing or not? The second question has to do with efficiency of fuzzers. Is there some fuzzer out there that is a faster implementation overall? If yes, which one it is, and possibly why is this the case? The third question has to do with consistency of fuzzing. Are there any fuzzer implementations that are able to expose some of the bugs in most or all of their runs even? To answer the question, we have run many experiments. The paper reports them in tables like the one that you see here. Again, there are too many numbers here, so don't try to read them. But the point to take is that each of the rows focuses on some particular bug, and its entries show results from 10 24-hour runs of each fuzzer hunting for a particular bug. For example, in the last two rows here of this table, we see that AFL, using GCC as the compiler, was able to detect the first of these bugs in 7 out of the 10 24-hour trial runs in 10 hours and 46 minutes on average. On the other hand, the same fuzzer, AFL, was not able to detect the second bug, the last bug here, in any of its 24, in its 10 24-hour runs. We also see that the first few bugs are relatively easy. Most tools detect them in all runs, but some tools, those in yellow, are significantly faster than others. Finally, note that as we move down lower in the table, bugs start becoming quite challenging for most of the tools. In particular, the last bug is not detected by any of the tools in the 10 24-hour runs that each of them is running. On our paper, you can see more tables, like the second one shown here, which shows results starting from fuzzing campaigns from the 6-low pan layer of Contiki-NG. Again, notice that as we move lower in the table, bug starts becoming considerably harder to expose for all the fuzzers. In a nutshell, the answers to the 3 research questions that we have asked are the following. We did not detect any clear superiority of hybrid fuzzers with respect to ability to expose bugs compared to mutation-based fuzzers. No fuzzer is uniformly superior than to all the others. On the other hand, there are 3 fuzzers, namely MOPT, SIMCC, and QSIM, that stand out in terms of their ability to expose bugs fast and also doing so more consistently. So a lesson that we have learned is also that the consistency and effectiveness of a hybrid fuzzer is strongly dependent on the consistency and effectiveness of the mutation-based component. This is not particularly surprising once you think about it. A bonus research question that our paper answered in the second part is to investigate an additional question related to the use of sanitizer when fuzzing. It's folklore knowledge that sanitizers are able to explore bugs more easily and also triage bugs more accurately. On the other hand, sanitizers impose a considerable runtime overhead. We actually measured an overhead of 12 times when using address sanitizer. This roughly means that fuzzing code instrumented by a sanitizer for a day will explore the same number of runs that a fuzzer without sanitizer instrumentation is able to explore in just 2 hours. So using sanitizers is a trade-off. And there are very few published works that investigate this trade-off. So the last question that we wanted to answer is, do sanitizers pay off for the runtime overhead in terms of exposing more vulnerabilities within a given time limit? Once again, we answer this question with a series of experiments. We first evaluate running the fuzzers on code that has been instrumented by Yasan, the address sanitizer. You can find the complete set of results in the paper, but the interesting tables are the ones that show differences like the one shown on this slide. A green up arrow followed by some time quantity means that the fuzzer detected the bug the same number of runs, but faster with the time quantity shown using the sanitizer than without. A red down arrow, on the other hand, means that the results using the sanitizer were worse, either in the number of times the bug was detected or in the time that this took. Finally, there are entries that show that the bug was detected more times with a sanitizer than without. You can find many more tables in our paper. If we only look at this table for address sanitizer, This table paints a bleak picture. Overall, all fuzzers have deteriorated with respect to their ability to detect these bugs. The situation changes if we consider fuzzing from the 6-low pan layer. We see many more green entries than red ones. We repeated the same experiment using effective SAN, the effective type sanitizer. Here, the results are overall more positive. Not only is bug detection more consistent, but there are bugs that are detected only when using effective type sanitizer. Refer to our paper for more information. We strongly recommend effective type sanitizer. So as answer to research question 4, sanitizers make detection of easy to expose bugs slower generally. On the other hand, they make fuzzers more consistently detecting bugs. And most importantly, they are crucial for detection of difficult to expose bugs and vulnerabilities. Overall, we find that sanitizers pay off for their non-negligible overhead once the easy to fix bugs have been fixed. The easy to locate bugs have been fixed. I refer to our paper for more tables and experiments, more lessons learned, more suggestions on how to compare fuzzers, related work, and also about how to access our paper's artifact, which allows one to repeat our experiments if they so wish, or to add more fuzzers into them and compare them with a baseline. In summary, this paper has used 8 state-of-the-art fuzzers, half of which are mutation-based and half of which are hybrid fuzzers, to investigate research questions regarding the effectiveness, efficiency, and consistency of fuzzers. We have answered these questions using results from bug hunting fuzzing campaigns, using real code vulnerabilities that we have found and fixed over a period of about 3 years in a code base, in the code base of Contiki-NG. We have also investigated the impact that 2 sanitizers, address sanitizer and effective type sanitizer, have on these fuzzers. Our advice is to start fuzzing a code base first without a sanitizer, fix one bug at a time, and start using sanitizer-aided fuzzing once the easy to locate bugs are out of the picture. As the title of the paper says, there are so many fuzzers to try and so little time, and the time for this presentation has ended. Thank you for your attention.